Octet rule exceptions in Lewis structures. The octet rule states that compounds are stable and ionic and covalent when there's 8 electrons in the valence shell. So when making ionic or covalent compounds, when things are reacting, the goal is always to become stable, unreactive. And that is when there's 8 electrons in the valence shell, in the outermost shell. Now, sometimes based off of size and elements and orbitals, like talked about previously, where the electrons exist, there can be a few exceptions. So let's look at the first one, creating a Lewis structure, and stating the shape. Knowing that when we draw a Lewis structure, it's a 2-dimensional representation where the valence electron repulsion theory tells us, because electrons are in bonds and they repel each other, what the 3-dimensional shape actually is of particular molecules. So all of these molecules stated here are covalent. Let's look at the structure, define octet and exceptions, and state the shape. So BH3. So boron is right here on the periodic table, and then we have hydrogens. So I have 3 valence electrons plus 3 times 1, since each hydrogen has 1, which gives me a total of 6. So your central atom is always the one that can make the most bonds, or where there's more of others, they're going to surround the central. Here, boron can make 3 bonds, hydrogen can only bond once. So I'm going to place boron in the middle and my hydrogens around. Now, a good rule of thumb is always to connect the atoms first and then take that away from the total amount of electrons that you have. No, you can always draw the valence electrons and then connect the dots. It's kind of whatever way works for your interpretation the best. I believe that I know hydrogen has to bond to boron all 3 times, each of the hydrogens. All right, so I have no more elements. Now, usually you want to satisfy the octet. So we know that helium and hydrogen are happy with 2. Since they only have an s orbital, the s orbital with 2 electrons is satisfied, becomes unreactive. So hydrogen is satisfied in this structure. Now I have 2, 4, 6 electrons in the total atom, and I only have 6 for the structure, so I don't have any more electrons to give or take. However, boron does not have 8. So most of the time, students will say, all right, well then there needs to be a double bond. But this is not possible because hydrogen cannot have more than 2. Hydrogen only has an s orbital. Here comes the first exception. When in period 2, usually up to boron, you can have less than 8 valence electrons to be happy. So you would be satisfied here. Once you get to carbon, nitrogen, so on in period 3, you have more room for electrons, so therefore you can have 8. Now the difference between boron and carbon, some may say, well, what's the difference between boron and carbon? That's because boron has 3 valence electrons, carbon has 4. So because carbon can bond 4 times, that's already 8 valence electrons. Boron can only bond 3, and there's no lone pairs, so it can only have 6 to be unreactive. So the exception is that once you get to boron, or before it, you can have less than 8 valence electrons. So now let's look at the shape. I have 1, 2, 3 electron groups, 3 bonding groups, and 0 non-bonding. So my molecular shape, if I look down here, is 3, 3, bonding, 0, non-bonding, trigonal planar. Alrighty, now let's look at another one. PCl3. So I have phosphorus and chlorine. Phosphorus is here, chlorine is right here. Phosphorus has 5 valence electrons, and I have 3 chlorines, each of which has 7. So it's 5 plus 21, which is 26 valence electrons. So phosphorus can bond 3 times. Chlorine can only bond once, so the chlorines are going to go around phosphorus. Now, I like to just connect my chlorines. Now, I know that phosphorus is not happy. Phosphorus is not even in period 2, it's in period 3. So I know it's not an exception of being able to have less. I have to satisfy the octet. However, chlorine, if we look at chlorine by itself, has 7 valence electrons. It can only bond once. So the chlorines are happy. Now, 2, 4, 6. We use 6 of our electrons, so we have 20 left over. I'm going to satisfy the chlorines right now to make sure that they're satisfying the octet, since I know it can only bond once and I cannot make any more bonds. So now I give all my chlorines their electrons. So I gave 6 pairs of electrons, 3 pairs of electrons, 6 electrons in total to each chlorine, times 3 is 18. So I have 2 more electrons left over. That's going to go to phosphorus. Now you count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Perfect. Another thing that gives it away is phosphorus has 5 valence electrons. So it can only bond 3 times. So note that you always want to satisfy the octet, especially the one in the middle, but it depends on what it's bonding with. Chlorine, the halogens can only bond once. It is very unlikely for that lone pair to break. So therefore, bond 1, satisfy everything around it, and then check for the total number of electrons. So now let's look at the shape. 1, 2, 3, 4 electron groups. I have 4 things around the element. 1, 2, 3 bonding, and 1 non-bonding. Now the shape for that would be, let's look here. Total electron groups is 4, okay? 4 bonded, 0, that's not me. 4, 3 bonding, 1. There we are. Trigonal pyramidal is my shape. So think of electron groups as everything around the central atom. And then you specify bonding and non-bonding. Your bonding and non-bonding should always add up to the electron groups. Let's look at the last 2 over here. So we have SO2, sulfur and dioxide. So sulfur and oxygen can make the same number of bonds. But there's 2 oxygens and 1 sulfur, so the oxygens are going to go around the sulfur. How many total valence electrons do we have? 6 plus 2 times 6, 18. So sulfur, oxygen, oxygen. Now, I know that sulfur is going to bond once to both of the oxygens. Now, here's the difference then with the other examples. Oxygen, if we look at oxygen by itself, has 6 valence electrons. So oxygen can bond twice, and it wants to bond twice. So I'm going to create another bond right here, and now I have satisfied my sulfur. Great. So I've used 8 of the 18 electrons, so I have 10 left over. Now, I have 2 more oxygens, and if I want to satisfy those octets, I know that I have to give each 4 electrons. 2, 4, 6, 8. Great. However, now I still have 2 electrons left. So just like in the other example, that's going to go to sulfur. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So I have all my electrons. Now sulfur is in period 3. When you're in period 3, n is equal to 3, you have s orbital, p, and d. You know that the s orbital can have 2 electrons, the p can have 6, and the d can have 10. So you do have more room for multiple bonds and can disobey the octet and have multiple electrons. Now, that's an exception when you can't rearrange or fix it in any other way for the purposes of our class. We always want to satisfy, so if we can, we will always push to satisfy the octet. So even though sulfur is another exception, I can move the electrons from this bond to one of the oxygens. And then it would look like this. So now each oxygen has 8 and the sulfur only has 8, and I have my 26. And this would be 2 possible structures because it could also happen to the other oxygen. Now let's look at the shape. We have, looking at just the sulfur, 1, 2, 3 electron groups, 1, 2 bonding groups. Remember that even though this is a double bond, it counts as one group of bonds, and we have 1 non-bonding. So the shape 4, 3 electron groups, 2 bonding, 1 non-bonding is bent. Now let's look at one more. Let's erase this. Arsenic tetrafluoride. So let's see where all of that is. So we have fluorine and arsenic. All right, arsenic is in group 5, fluorine is in group 3. And this should be fluorine 5, actually. Let's fix that. So arsenic is in group 5, if we all see that right here, and fluorine is in group 7. Okay. So how many total electrons do we have? Arsenic is 5. Fluorine is 7, and we have 5 of them. 5 times 7 plus another 5. What does that come out to be? It's always good to count your electrons first before bonding things together. So that should be 40 electrons. So now, all right, I have arsenic. That's going to go in the middle. Fluorine, 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 fluorine. 1, 2, 3, 4, 5. 5 fluorines. And then I know that the fluorines have to bond to the central atom. They absolutely have to. Now, 2, 4, 6, 8, 10, I already disobeyed the octet. Let's see where arsenic is. Arsenic is in period 4, so it's below period 3. It has sp,d, and the f orbital, so it definitely has more room for electrons. Now, the difference between this example and sulfur dioxide is there's no way for us to rearrange to obey the octet. The 5 fluorines have to bond to the arsenic because that's the compound, so it has to disobey the octet. Now, we have to satisfy fluorine with the octet, so let's place all the electrons around fluorine. So 6 around each one. And then we count our total electrons. So arsenic is satisfied because it is below period 3, and it has to bond to 5 fluorine, so there's no way for us to rearrange the molecule for it to obey the octet. It has up to 4 orbitals, sp, d, and f. Since it's n is equal to 4, we have sp, d, f. And then fluorine, period 2, cannot disobey the octet, has to have 8. So let's count our total electrons. 2, 4, 6, 8 times 5, that's 40. Great. So you're finished. Now, the shape of it is a little trickier because it's not on this chart, and you do not have to know up to 5 electron groups, but you would look at, for 5 electron groups, what the shape is for this structure. But here, it's how the breakdown of the octet, when you can disobey it or not, going below or above 8 electrons, and how to maneuver things around to obey the octet, count the amount of electrons bonding and non-bonding groups to then figure out